Basics of Artificial Intelligence, Episode 1. Artificial Intelligence, Understanding it from the Ground Up. Hello everyone. Today we are going on a journey that could truly change the way you see the world. Artificial intelligence, it is not just a word, it is a revolution that is happening right now at this very moment. And today you and I together will understand this entire world from absolute zero all the way to engineering level. So get ready, grab your coffee and let us begin. Chapter 1. What is artificial intelligence? First of all, a simple question. If I asked you what is intelligence, you would say understanding things, learning, solving problems, making decisions. Exactly right. So artificial intelligence means putting all of these capabilities inside machines, making computers capable enough that they can think, learn, understand, and act just like a human being. John McCarthy first coined this term in 1956, artificial intelligence. He defined it as the science and engineering of making intelligent machines. From that point to today, the world of AI has grown so much it is truly astonishing. AI versus human intelligence. Now let us make an important comparison. What is the difference between a human and AI? A human learns from experience. A baby falls, gets up, falls again, and eventually learns to walk. No program needed. For a machine to learn, it needs data. Hundreds of thousands of examples, patterns, feedback. A human feels emotions. A machine so far can only simulate emotions. A human can do many things well. A machine in one specific task can outperform any human. But generalizing across everything, that is still largely a human ability. Types of AI: narrow, general, and super. Now understand AI at three levels. First, narrow AI, also called ANI, artificial narrow intelligence. It does only one thing, just one. But in that one thing, it is the best. For example, Google search engine only searches, YouTube recommendation system only suggests videos. Chess playing AI like Deep Blue only plays chess. Every AI we use today is narrow AI, GPT-2, Siri 2, Alexa 2. Second, general AI called AGI, artificial general intelligence. This is the stage where a machine can think exactly like a human being in every domain. Whatever it needs to learn, it learns. Whatever it needs to do, it does. As of now, AGI does not exist. It is a future goal. Researchers are working hard on it. Third, super AI, AZ, artificial super intelligence. This is the level where AI becomes far more intelligent than any human in every field. Science, medicine, art, philosophy, everything. Elon Musk said, as it could be humanity's greatest risk and also its greatest opportunity. Right now we are at the first level, narrow AI, and even this is incredibly powerful. Chapter 2. The history of AI. The story of AI is absolutely fascinating. Let us go back in time. 1950, Alan Turing, and the question, the year was 1950. There was a mathematician, Alan Turing, a true genius. He wrote a paper, Computing Machinery and Intelligence. And he asked one question, can machines think? And then he proposed a test, the Turing test. In the Turing test, a human interacts with a computer through text. If the human cannot tell whether they are talking to a machine or another human, then the machine is considered intelligent. A simple concept, but an extremely powerful idea. 1956, the Dartmouth Conference. In 1956, John McCarthy organized a conference at Dartmouth College. For the first time officially, the name artificial intelligence was given to this field. Everyone was excited. It seemed like intelligent machines would be built within 10 to 20 years, but it was not that easy. The AI winters, a few years later, problems started appearing. Computers were slow, data was scarce, algorithms were weak, funding stopped, research slowed down. These periods came to be known as AI winters. The first AI winter came in the 1970s. The second came at the end of the 1980s. But even then, people kept working, slowly but steadily. 1997 Deep Blue. In 1997, a historical event took place. IBM's Deep Blue defeated world chess champion Garry Kasparov. The entire world was stunned. A machine had beaten a human at chess, a game of intellect. It was a true turning point. 2012, the deep learning revolution. Then came 2012. There was the ImageNet competition. The task was to classify images. A deep learning model called AlexNet delivered dramatically better performance than anything before it, reducing the error rate from 26% to 15%. And everyone said this deep learning thing is incredible. This is where the era of modern AI truly began. 2016 AlphaGo. In 2016, Google DeepMind's AlphaGo defeated Go world champion Lee Sedol 4-1. The game of Go has far more possibilities than chess. Brute force does not work. Strategy is needed. Intuition is needed. AlphaGo proved that AI can be taught intuition as well. 2022 to 2023, ChatGPT and the AI boom. And then came November 2022. OpenAI launched ChatGPT, 1 million users in just 5 days, 100 million in 2 months. The entire world started talking about AI, students, teachers, doctors, lawyers, artists, everyone, and this is when AI truly went mainstream. Chapter 3, Machine Learning, the heart of AI. Now we come to the most important part, machine learning. This is the core of AI, the heart. What happened in traditional programming? You gave input, you gave rules, you got output. For example, if temperature is greater than 100 degrees, then print water is boiling. We wrote the rules manually. But in machine learning, you give input, you give output, the machine figures out the rules on its own. This concept is revolutionary. The three main categories of ML machine learning works in three fundamental ways. Supervised learning. In supervised learning, data is labeled, meaning there is a teacher, someone who provides the correct answers. Example, you have 10,000 photos. Some have dogs, some have cats. Each photo has a label, dog or cat. The machine learns from these photos, it understands patterns, and when a new photo arrives, it tells you on its own, this is a dog or this is a cat. Examples of supervised learning: spam detection, email filtering, medical diagnosis, stock price prediction. Algorithms used: linear regression, logistic regression, decision trees, random forest, support vector machines, neural networks. 2. Unsupervised learning. Here there is no teacher. Data is not labeled. The machine finds patterns on its own. For example, a company has 1 million customers. You want to divide them into groups. No labels exist. The machine groups similar customers together on its own. This process is called clustering. What Netflix or Spotify recommends to you uses data from users similar to you. This is part of unsupervised learning. Algorithms: K-means clustering, hierarchical clustering, DV-scan, PCA, which stands for Principal Component Analysis. 3. Reinforcement learning. This is the most fascinating concept. Imagine a child is learning to ride a bicycle, falls down, gets up, tries again. When they do it right, there is joy, a reward. Reinforcement learning works exactly like this. There is an agent, there is an environment. The agent takes an action. The environment gives a reward or a punishment. The agent learns how to get the maximum reward. AlphaGo learned this way, playing millions of games against itself. Reward for winning, penalty for losing. Self-driving cars also learn through reinforcement learning. Overfitting and underfitting. Now an important concept: overfitting and underfitting. Imagine a student who memorized only the questions from previous exams, did not understand the concepts, a new question came in the exam and they failed. This is overfitting. The model performs very well on training data, but fails when new data arrives. And underfitting, the model is so simple that it does not even perform well on training data. The student did not study at all. The perfect model is one that generalizes, performs well on both training and testing. This is called the bias variance trade-off. Training, validation, and test data. In machine learning, data is split into three parts. Training data, 70% the model learns from this. Validation data, 15%. This is used to tune the model to adjust hyperparameters. Test data, 15%. The final exam, the model has never seen this data. We evaluate its performance here, and sometimes we use cross-validation, k-fold cross-validation, divide the data into k parts, repeatedly use different training and validation sets. A more reliable result. Chapter 4, Neural Networks, Mimicking the Brain. Now we come to neural networks. You have heard this term, neural network. It is inspired by the human brain. Our brain is made of neurons, billions of neurons, all connected to each other. When a signal arrives, neurons activate, information flows. Artificial neural networks have a similar structure built in software. The structure of a neural network has a minimum of 3 layers. First, the input layer. This is where data enters. If we are classifying images, pixels are the input. If text, words or characters, in the middle, hidden layers. This is where the real work happens. Learning patterns, extracting features. The more hidden layers there are, the more complex things the model can learn. Last, the output layer. The final answer comes from here. Dog or cat, spam or not, positive review or negative. How a neuron works. What does an artificial neuron do? It takes inputs. Each input has a weight associated with it. It multiplies and adds them all together, then applies an activation function and gives an output. Mathematically, output equals activation of the sum of weight times input plus bias. Weight and bias. These are the things that get learned. They get adjusted during training. Activation functions are extremely important. They add non-linearity. Without an activation function, a neural network can only do linear transformation. It cannot learn complex patterns. Popular activation functions are sigmod. Output between 0 and 1 was used in binary classification. Now, less popular, ReLU, rectified linear unit. If the input is positive, pass it through as is. If negative, make it 0. Simple, fast, most widely used today. 10. Output between -1 and +1. Better performance than sigmod. Softmax used in the output layer for multi-class classification. All outputs sum to 1 gives a probability distribution, backpropagation, the learning process. Now the most important process, backpropagation, this is what teaches a neural network. Understand it this way, the network made a prediction, it was wrong, so calculate the error, the difference between actual and predicted. Now propagate this error backwards from the output layer to hidden layers, from hidden layers to the input layer. Slightly adjust each weight so the error decreases. Repeat this process thousands of times, millions of times. Gradually the weights settle in the right place. The network learns. This optimization process is called gradient descent. Gradient descent is an optimization algorithm. Imagine there is a mountain. It is dark. You need to get to the bottom. What would you do? Place your foot whichever direction is steepest going down. Take one step that way. Check again. Take another step and eventually you reach the valley. Gradient descent does exactly this. It tries to reach the minimum of the loss function. Learning rate is a hyperparameter. It determines how big each step is. Too large, you overshoot. Too small, extremely slow. Variants include stochastic gradient descent, mini batch gradient descent, Adam optimizer, RMS prop. Adam optimizer is the most popular today. It automatically adjusts the learning rate. Chapter 5, Deep Learning. Going deeper inside machine learning, there is an even more powerful field. Deep learning, this is essentially a neural network with many hidden layers. Deep means more layers. When there are more layers, the model can learn more complex patterns. A simple neural network might learn lines and curves. A deep network can learn faces, objects, and entire scenes. CNN, convolutional neural networks for images. CNN is the best. CNN has a special layer, the convolutional layer. This layer applies a filter over the image. A small window slides across the entire image. It looks for features, edges, corners, textures. The early layers see basic features, horizontal lines, vertical lines. Middle layers see combined features, eyes, noses, ears. The final layers see complete objects, faces, cars, dogs, CNN applications, image classification, object detection, face recognition, medical image analysis, self-driving cars. Famous CNN architectures: LeNet, AlexNet, VGG, ResNet, Inception, EfficientNet, RNN, recurrent neural networks, CNN for images, RNN for text and sequences. RNN has memory. Previous information is retained, like I love eating blank. Your brain filled that in from context from the previous words. RNN does the same. It processes a sequence. At each step, it considers the previous state. Problem: RNN forgets long-term dependencies. Very old information fades away. LSTM, long short-term memory. LSTM is the solution to this problem. LSTM has special gates. For get gate, what to forget, input gate, what new information to remember, output gate, what to output right now. These gates together decide what information to keep and for how long. LSTM applications, language translation, speech recognition, text generation, time series prediction, transformers, the game changer in 2017, a revolutionary paper was published, attention is all you need. It introduced the transformer architecture. The transformer overcame the limitations of RNN. It can process an entire sequence at once in parallel, and it introduced a new concept, the attention mechanism. Attention mechanism means automatically learning how important each word is compared to every other word. Like the animal did not cross the street because it was too tired. Here it refers to animal. The attention mechanism figures this out. The transformer is what powers BERT, GPT, ChatGPT, Gemini, Claude, every modern language AI. Chapter 6, Natural Language Processing. Now a very exciting area. NLP, Natural Language Processing, making computers understand and process human language. That is the job of NLP. Language is very complex. Words have multiple meanings. Context matters. Sarcasm exists. Grammar is intricate. NLP handles all of these challenges. Basic NLP concepts. First, understand tokenization, breaking text into smaller parts, into words or subwords or characters. Example, the sky is blue. Tokens would be the sky is blue. Then stop words removal. Remove common words that do not add much meaning. The is, are, and these are stop words. Then stemming and lemmatization, bringing words to their root form. Running becomes run, better becomes good. Then part of speech tagging, identifying the grammatical role of each word, noun, verb, adjective, adverb, then named entity recognition or NER. Identifying names of people, places and organizations. Elon Musk is a person, OpenAI is an organization, San Francisco is a location. Word embeddings, computers understand numbers, not words, so words need to be converted into numbers. Word embeddings do exactly this. Each word is represented as a vector, a list of numbers. The magical property is that similar words have similar vectors. King minus man plus woman equals queen. This vector arithmetic actually works. Famous word embeddings word 2x, glove, fast text, and modern models have context-dependent embeddings from BERT. The same word in a different context gets a different embedding. Large language models, LLMs. Now we come to LLMs. Large language models, ChatGPT, Gemini, Claude, Llama. These are all LLMs. They are based on transformer architecture. They have billions of parameters. They are trained on terabytes of internet data. GPT-3 has 175 billion parameters. GPT-4 has even more. These models are trained on a simple task, predict the next word. But because of the enormous amount of data and parameters, these models become remarkably intelligent. They can write code, create stories, answer questions, translate languages, summarize documents, fine-tuning and RLHF. To make a pre-trained LLM even more useful, we do fine-tuning. We take data for a specific task and train the model a bit further. And then there is RLHF, reinforcement learning from human feedback. ChatGPT was trained using these human raters, rated the model's responses, helpful, harmless, honest, and the model learned what kind of answer it should give. This is why ChatGPT feels so natural and helpful. Chapter 7, Computer Vision. Eyes without a brain are useless. A brain without eyes is blind. Computer vision gives AI its eyes, teaching machines to understand the visual world. That is computer vision, image classification. The most basic task, which category does this image belong to? Cat or dog, car or bike, tumor or healthy tissue. CNN is perfect for this task. Real applications, Google Photos, automatically tagging faces, Instagram filters, medical X-ray analysis, object detection, not just classifying an image but also locating things within it. What is where in this image? Drawing bounding boxes around objects. YOLO, you only look once, is a famous algorithm. It does real-time object detection extremely fast. Used in self-driving cars to detect pedestrians, traffic lights and other vehicles. Image segmentation, object detection gives bounding boxes, segmentation gives pixel level accuracy, every pixel is assigned a class, this is sky, this is road, this is a person, heavily used in medical imaging, exactly how much of the tumor exists and exactly where. GANs, generative adversarial networks, now a mind-blowing concept, GAN. Proposed in 2014 by Ian Goodfellow. There are two networks, generator and discriminator. The generator creates fake images. The discriminator judges real or fake. The generator's goal is to fool the discriminator. The discriminator's goal is to catch it. Both keep improving together. Eventually, the generator becomes so good that the fake images look completely real. Deepfakes are made with this technology, and AI art generators are also based on this concept. Diffusion models. These days, diffusion models are even more popular than GANs. Stable Diffusion, DAW-LE, Midjourney, these are all diffusion models. The concept is during training, gradually add noise to images and let the model learn how to reconstruct the image from that noise. During inference, start with pure noise. Gradually remove the noise, an image emerges, give it a text prompt, and an image is generated. It feels like magic, but it is mathematics. Chapter 8, Important AI Concepts and Terminology. Now, there are some important terms that every AI engineer must know. Let us go through them one by one. Parameters and hyperparameters. Parameters, these are the values that get learned inside the model. Weights and biases, they are automatically updated during training. Hyperparameters, these are set by us manually. Learning rate, number of layers, batch size, epochs, they are set before training begins. Hyperparameter tuning, finding the best hyperparameters using grid search, random search, or Bayesian optimization. Batch size and epochs. Batch size, how many training examples to process at once, processing the full dataset at once. Batch gradient descent, one example at a time. Stochastic, a few examples, mini batch. Epoch 1, complete pass over the entire training data. 5 epochs means the model has seen the training data 5 times. Loss function, the loss function tells us how wrong was the model's prediction. We want to minimize the loss. For regression, mean squared error, mean absolute error. For classification, cross entropy loss, binary cross entropy. Regularization, the technique to prevent overfitting. L1 regularization, also called lasso. Some weights become 0, feature selection happens automatically. L2 regularization, also called ridge. Weights become smaller but do not become 0. Dropout, randomly disable some neurons during training. The model becomes more robust. Batch normalization, normalize the output of each layer. Training becomes faster and more stable. Confusion metrics and evaluation metrics. How do we measure how good a model is? Confusion metrics, a table of actual versus predicted. 4 cells, true positive, true negative, false positive, false negative. Accuracy out of everything, how many were classified correctly? True positive plus true negative divided by all. Precision of those predicted positive, how many were actually positive? True positive divided by true positive plus false positive. Recall of those that were actually positive, how many were correctly identified? True positive divided by true positive plus false negative. F1 score, the harmonic mean of precision and recall. When you need both balanced, OCROC measures the model's overall ability to distinguish between positive and negative. Transfer learning, another very powerful concept, transfer learning. First train a model on a large data set. This becomes a pre-trained model. Then fine-tune it for your specific task with much less data and time. Like take ResNet trained on ImageNet and fine-tune it to classify medical images. Models like GPT are also pre-trained. We can fine-tune them for different tasks. Because of transfer learning, smaller companies and researchers can also build powerful AI without enormous resources. Chapter 9, Real-World Applications of AI. Now let us see where exactly is AI being used today. Healthcare, AI in medical imaging, analyzing X-rays, MRI scans, CT scans, detecting tumors, detecting retinal diseases, drug discovery, finding new medicines with AI. What normally takes decades can happen in years. AlphaFold DeepMind's project, it predicts protein structures. This is a revolution in biology. Personalized medicine, suggesting treatment based on a patient's genetic information and medical history. Self-driving cars, computer vision, sensor fusion, reinforcement learning all work together. Cameras, LiDAR, radar data comes from multiple sensors. Real-time processing, decisions in nanoseconds, braking, steering, lane changing. Tesla, Waymo, Cruise, all are in this race. Finance, fraud detection, automatically detecting abnormal transactions. Algorithmic trading, AI buys and sells stocks in milliseconds. Credit scoring, AI decides whether a loan should be given or not. Risk assessment, calculating the risk of a portfolio. Entertainment, Netflix's recommendation system, 80% of viewership comes from recommendations. Spotify's Discover Weekly, AI powered. AI music generation, Suno Udio. AI art, Midjourney, DALL-E, Stable Diffusion. AI video generation, Sora, Runway, Pika. Education, personalized learning paths, identifying weak areas. Adaptive quizzes, AI tutors available 24 hours a day, 7 days a week. Infinite patience, automated grading. Content generation for courses. Agriculture, crop disease detection from drone images. Weather prediction and irrigation optimization, yield prediction, precision farming. Chapter 10. Ethics and the dark side of AI. With great power comes great responsibility. This chapter is a bit serious but extremely important. Every AI engineer must understand this. Bias in AI. AI models learn from data. If the data is biased, the model will be biased too. Amazon built a hiring AI. It started automatically rejecting women candidates because the historical hiring data had mostly men. Amazon shut down that system. Facial recognition systems have lower accuracy for black individuals because there was not enough diversity in the training data. This bias becomes real-world discrimination, loan rejections, job denials, wrong arrests. Deepfakes, GAN technology can create realistic fake videos of anyone, fake speeches of political leaders. Celebrity deepfakes, spreading misinformation. This is a serious threat to democracy and personal privacy. Privacy AI systems collect enormous amounts of data, location, browsing history, conversations, surveillance capitalism. Companies earn money by selling your data. China's social credit system, monitoring people using AI, rewards and punishments. Job displacement, AI automation is replacing many jobs. Manufacturing, data entry, customer service, some creative work, all are being impacted, but new jobs are also being created. AI trainers, prompt engineers, AI ethicists, data scientists. The transition can be painful, especially for those who do not have new skills. AI safety, in the long term, we need to think about AGI and ASI. The alignment problem, aligning AI's goals with human values. If a highly intelligent AI's goals are not aligned with human values, the consequences could be extremely dangerous. Anthropic, OpenAI, DeepMind, all are working on AI safety research. This is a very important and still open problem. Chapter 11. AI tools and frameworks. Now, let us come to the practical side. If you want to work in AI, what do you need to learn? Programming language, Python, full stop. Python is dominant in AI and ML. The syntax is simple. There are countless libraries. The community is massive. Learn the basics, variables, loops, functions, classes, file handling, then learn NumPy, numerical computations, arrays, matrix operations, then pandas, data manipulation, data frames, CSV files, data cleaning, then matplotlib and seaborn, data visualization, ML libraries, scikit-learn for classical ML algorithms, linear regression, random forest, SVM, K-means, all in one library. Perfect for beginners. TensorFlow by Google production grade. Mobile and web deployment. TensorFlow Lite and TensorFlow.js, PyTorch by Facebook. The researchers' favorite dynamic computation graph, easy to debug. Keras built on top of TensorFlow, high-level API, easy for beginners. Hugging Face, a hub for pre-trained models. The Transformers library, thousands of models available. Fine-tuning made easy. Cloud platforms. You need a GPU for training. They are expensive. Use the cloud. Google Colab free GPU notebook environment. The best starting point for beginners. AWS SageMaker production grade ML platform. Google Cloud AI platform. Microsoft Azure ML Kaggle competition platform. free GPU, public datasets. Every ML learner should have an account here. MLOps building an AI model is one thing, deploying it in production is another thing entirely. MLOps, machine learning operations, from model development to deployment and monitoring, ML flow, weights and biases, Kubeflow, Docker, Kubernetes, model versioning, experiment tracking, deployment pipelines, monitoring, retraining. A complete AI engineer knows MLOps as well. Chapter 12, Advanced Topics. Now let us venture into more advanced territory. These concepts are extremely hot right now. Prompt engineering, the art of carefully designing prompts to get the best results from LLMs. Zero shot, no examples. Just do the task directly. Few shot, providing a few examples. The model understands the context from them. Chain of thought, telling the model to think step by step. Let us think step by step. This is very helpful in complex reasoning. React reasoning plus acting. The model thinks, takes an action, observes, then thinks again. Prompt injection attacks malicious prompts that make the model do the wrong thing. A genuine security concern. RAG retrieval augmented generation. One problem with LLMs, knowledge cutoff. They do not know about events after their training. RAG is the solution. A user's question arrives, first retrieve relevant documents from a database or the internet, then give those documents as context to the LLM and generate an answer. This way the LLM can use up-to-date information. ChatGPT's browsing feature is based on this exact concept. Multimodal AI. Earlier, AI could only handle one type of input, either text or images. Multimodal AI handles multiple types at once. Text, images, audio, video, all together. GPT-4 can take both image and text as input. Gemini is also multimodal. This makes AI far more powerful and genuinely useful. AI agents after LLMs, the next evolution is AI agents. An agent is an autonomous AI that can take multiple actions to complete tasks. A user says, book me a flight. The agent does searches the internet, compares options, selects the best one, completes the booking. AutoGPT LangChain agents, OpenAI Assistants API, these are all frameworks for building AI agents. Memory planning, tool use, these three capabilities make an AI agent powerful. Federated learning, privacy preserving ML. Instead of collecting data in one place, train locally on each device, only send model updates to the central server. Google's good keyboard improves using this. Your typing patterns stay on your phone. Quantum machine learning, a glimpse of the future. Quantum computers are exponentially faster than classical computers for certain problems. Quantum machine learning, combining quantum computing with ML. Currently in the experimental stage, but the potential is enormous. Chapter 13, the future of AI. Now a look at the future. These are predictions. Nobody knows exactly, but from current trends, we can make informed guesses. AGI, when will it arrive? Geoffrey Hinton, considered the godfather of neural networks, has said that AGI could arrive in 5 to 20 years. Other experts say it will take much longer, or perhaps it will never arrive in the way we imagine. But look at the progress. Every year models are getting dramatically better. The rate of progress appears exponential. AI and human collaboration in the near future. Likely AI will not replace, it will augment. Doctors will diagnose better with AI. Lawyers will research better with AI. Engineers will write better code with AI. Human plus AI. This combination will outperform either human alone or AI alone. Regulation and governance. Governments have started regulating AI. The EU's AI Act, a comprehensive law, strict rules on high-risk AI systems. US, UK, India all are formulating their own policies. A balance is needed. Do not block innovation, but harm must not be allowed either. AI and creativity. Can AI be creative? AI is composing music, writing poetry, creating art, writing screenplays. But is it truly creative? Or is it just recombining patterns? A philosophical debate. But practically the output is amazing. Artists, musicians, writers, those who use AI as a tool will thrive. Those who do not may fall behind. Chapter 14, Learning Path and Career Guidance. And finally, if you want to build a career in AI, what should you do? Foundation mathematics, you need math to understand AI, linear algebra, vectors, matrices, matrix multiplication, eigenvalues, the backbone of neural networks, calculus derivatives, partial derivatives, the chain rule. This is how backpropagation works. Probability and statistics, distributions, Bayes theorem, hypothesis testing, used everywhere in ML. Do not think mathematics is too hard. Resources today are excellent. 3 Blue 1 Brown on YouTube, the best visual explanations, Khan Academy, free and complete. Programming skills, you need to be fluent in Python, meaning you know how to code and you can get things done just by reading library documentation. Data structures and algorithms basics, lists, dictionaries, sorting, searching, object-oriented programming, classes, inheritance, polymorphism, SQL extracting data from databases, version control, Git, always use it, practical path, first step learn Python, 1 to 2 months, Kaggle, learn or free code camp. Second step, brush up on math, linear algebra, calculus, probability, 2 to 3 months in parallel. Third step, ML basics, Andrew Ng's machine learning course on Coursera. It is the best, a classic. Fourth step, deep learning fast.ai or the deep learning.ai specialization. Fifth step, build projects. Participate in Kaggle competitions, put them on GitHub. Sixth step, specialize, NLP, computer vision or reinforcement learning. Choose one area, go deep. Seventh step, read papers, arXiv, follow the latest research. This is important. Job roles in AI, data scientist, analyzing data, building models, extracting insights, machine learning engineer, building and deploying models, more engineering focused, data engineer, building data pipelines, collecting, cleaning and storing data, AI research scientist, developing new algorithms. A PhD is usually helpful here. MLOps engineer, maintaining models in production. Prompt engineer, effectively using LLMs. A new role, growing fast. AI product manager strategy and roadmap for AI products. Conclusion and a new beginning. By this point, you have learned a tremendous amount. What AI is, where it came from, how machine learning works, the structure of neural networks, deep learning architectures, NLP, computer vision, ethics, tools, career paths. This entire episode was a door into a vast world. The real work begins now, writing code, building projects, running experiments, failing, learning, growing. In the field of AI, one thing is certain, this field is not stopping. New models every week, new breakthroughs every month. Those who keep learning will stay relevant, stay curious, keep experimenting, stay in the community, teach others. And remember, AI is a tool, the most powerful tool humanity has ever created. But the tool is in human hands, in your hands. Understand this tool, control it, use it responsibly, make the world better. Thank you. See you in the next episode.